Hey, Johanna.
Hello,
How are you?
been good. You?
Doing fine too. Let's see. So today I'm gonna go over some of the wanting to see stuff first, and then I'll go over the stuff that you sent me earlier tonight. I saw the quiz PDF file that you sent.
Thank you.
Yep. Okay. Let's see. Let's see. Hey, Kimala. How are you?
Good. Thank you so much, by the way.
Yeah, no problem, no problem. Uh, so did you still need help with the problems that you sent me earlier, or did you want to go over some chapter 23 concepts?
Chapter 23, but also that one homework question that I sent you today.
Mm-hmm.
Um, no one knew how to solve it. So
Oh,
I don't
yeah,
know
yeah.
if perhaps you can solve it.
Let me try. Let me try.
And thank
Yeah,
you.
yeah. Let's see what this is about. Did you go to tutoring too? Did you ask
I
what that problem
did.
is?
I asked
Oh,
two
you
different.
did?
No one knew how to
Oh my
do
gosh. Let's see here. So, show how to carry out the transformation of benzene to chlorobenzene by going through a diazonium intermediate. At each step, either select the appropriate reagents or draw the correct product. So they gave us this empty benzene ring with no groups attached to it, reacting with HNO3 and H2SO4 nitration, which would give us product one. And then we have to put reagent two to give us uh, this aniline. And then when we react that aniline with NaNO2, HCl, that would give us product three. And then when we put that through reagent four, that would give us this chlorobenzene here. Right. So nitration would give us this NO2 on the benzene ring, but on the homework, they might want you to draw it in this form here, where the nitrogen is single bonded to an oxygen with three pairs of electrons and a negative charge, double bonded to an oxygen with two pairs of electrons, and the nitrogen will have a positive charge, a full charge of positive one on the nitrogen. Right. Um, so that's product one. Reagent two to convert NO2 into NH2 would be there's multiple reagents that could do that. We're going to reduce NO2 to NH2. So to do that, we have to use a reducing agent like H2PDC, iron HCl, or zinc mercury HCl. So one of those three reagents would be reagent two. And then when we have the aniline, which is a primary amine, and we react it with NaNO2 HCl, that's going to give us this diazonium salt here, where we have a triple bond between the two nitrogens here, where the nitrogen in the middle has a full positive charge. And then the nitrogen on top has one pair of electrons, which this is the best leaving group, one of the best leaving groups we have. So we could react it with like a lot of reagents to substitute that leaving group. We'll need nucleophile. And the nucleophile here is chlorine. So to do that, we have to use like CuCl, HCl, something like that. Um, so for your product one, try putting a positive charge on the nitrogen. You got the correct answer for reagent two, which they put zinc HCl. Um, for product 3, it is going to be this diazonium stop here with the nitrogen on the positive charge, but the homework didn't accept that, so you might want to try putting a chlorine with a negative charge somewhere.
Like
And
right next to it?
right next to it is the ideal place, but I think for your homework it could accept anywhere, right? For
Okay.
the CL. Yeah.
And why does it have a chlorine?
Yeah, a chlorine that comes from the HCl here, right?
Okay.
Because in some of the mechanism, something's gonna get protonated, kicking out a Cl minus, and that Cl minus is just gonna float around next to the positive charge here.
Okay.
Yeah.
And that should be it, right?
Wait, did they give you any feedback?
I exited out, so I can't see
Oh,
it
shoot.
anymore.
How
But
many
it's
attempts do
okay.
you have left?
I have a lot. We have 3 left.
3 left. Okay, 3 left. 3 left. I'm trying to figure out what other thing could this be. Product 3. Uh,
Okay.
let's
Let
see.
me try that out.
Yeah, try that out first. Don't forget the positive charge as well for the nitrogen in the product.
Oh yeah. No, for sure.
Yeah, try that out and then let's see. If it's not it, then I'm trying to figure out like it might have been a positive charge on that carbon, but not likely.
Oh my gosh, it worked. It was the chlorine. Thank you so
Oh,
much.
it was the chlorine.
No one knew
Yeah.
why it wasn't working. Oh my
Oh my
God.
god.
Thank you so much.
Yeah, no problem, no problem. And then now you can let them know like what was the problem, and then
Yeah, the chlorine. Who
save a lot
knew?
of headaches. Yeah, that's good. So now do you want to move on to chapter 23, Claisen condensation stuff?
That would be great. Yeah,
Yeah.
thank you.
Oh yeah, let's do that. Let's do that. Right. So now for Claisen condensation, that's gonna be very similar to aldol condensation from 118b, where the nucleophile is gonna be an enolate ion, right? But more specifically, the alpha carbon of the enolate ion. So for example, if I have this enolate ion here, we know that the negative charge on the oxygen is not the nucleophile, because when we do resonance, pushing the double bond, the negative charge to make a double bond between the carbon and oxygen, which pushes this double bond to make a negative charge on that carbon right there. The negative charge on the carbon is less stable, making it more reactive. So the nucleophile here would actually be this alpha carbon right here of the enolate ion. The electrophile will have to be the carbonyl carbon of an ester, right? Where the OR group of the ester is going to be considered the leaving group of the mechanism, of the Claisen condensation mechanism. The product of the Claisen condensation product is going to be a beta keto aldehyde or no, beta keto beta no. Let's say 1,3 dicarbonyl. 1,3 dicarbonyl. Right. Where you will have two carbonyls that have a 1,3 relationship with each other. 1, 2, 3, like that. And in most Claisen condensation, products is going to be a beta keto aldehyde or ester, meaning that one of the carbonyls will be an ester, like that. Where if this was the carbonyl carbon, this is the alpha carbon, that's the beta carbon, we could call this a beta keto ester. Beta keto ester, like that, in most Claisen condensation. But in all Claisen condensation, it's always going to be a 1,3-dicarbonyl, right? Which this is also a 1,3-dicarbonyl, but in most products, one of the carbonyls is an ester.
Okay.
Right. Okay. So there's 3 types of Claisen that you can have. You can have a self Claisen, a crossed or mixed Claisen, and you can have an intramolecular Claisen. And there's a specific name for the intramolecular Claisen condensation reaction, and that is the Dieckmann condensation. It's just a name for the intramolecular Claisen condensation. Okay, so if we look at the self-Claisen condensation, let's say we react this ester with these reagents here. First step is going to be NaOR, where the OR group is the exact same OR group as the ester. Second step, acid workup, H+ workup, right? The OR group here has to be the exact same as the OR group there. And I'll explain why at the end when I go over the 3 limitations for this mechanism. And then we'll move on to like the shortcut on how to predict the product quickly without having to do the whole mechanism. So when you have Na, always associate that with a positive charge, which means that whatever is attached to it is always a negative charge, like that. So our negative charge here is this OR minus, which is a strong base, right? Negative charge on oxygen, strong base. And this is a small base as well, where that strong base is going to look for the most acidic hydrogen. The most acidic hydrogen here is that alpha hydrogen, alpha to the carbonyl, because that can generate an enolate ion, right? Give us a stable conjugate base. So when we deprotonate that alpha hydrogen, we generate this enolate ion here, right? This hydrogen is not as acidic because when we deprotonate it, like let's say we deprotonate that hydrogen, we would get a negative charge on that carbon, which is not as stable as the negative charge here, because this negative charge cannot do resonance, right? Whereas the negative charge on the alpha carbon can do resonance, forming this enolate ion here. So once we generated our enolate ion, the alpha carbon of the enolate ion, that carbon right there, is going to be our nucleophile, right? And because this is self-Claisen, I'm going to bring in a second equivalent of an ester, right? Where the electrophile is going to be that carbonyl carbon right there. The partial positive charge of that carbonyl carbon is the electrophile, the dot carbon. Now, when I have the star attack the dot, I have to reform the carbonyl of the enolate ion, like forming that double bond between carbon and oxygen. And I know that if I were to draw out the resonance structure, the negative charge would go onto the carbon right there, right? And that would give us this resonance structure here, where the negative charge is on the carbon, and then that negative charge on the carbon can attack the electrophile, push the double bond onto the oxygen. But instead of drawing out the whole resonance structure, we know that the negative charge is already there, which can go for the attack right away without having to draw out the other resonance structure, pushing this double bond onto the oxygen like that. Does that make sense? Like on like why I didn't draw the other resonance structure?
Yeah.
Right. So now the next part here is going to be the confusing part, trying to combine those two molecules together. So the way that I'm going to do it here, it might not make sense. It might actually, let me just do it this way first, where most people see it in this way, and I'll show you the way that I do it because it's neater. I'm going to draw the exact same molecule as the top right here, which this is the star carbon right here, right? That star carbon made a new bond with this dot carbon, which that dot carbon is attached to an ethyl group, an O minus group, and an OR group like that. Right. Before it was double bonded to an oxygen, but now it's single bonded to an O minus because we popped that double bond onto the oxygen like that.
Okay.
So that's the way that most people see it on how to combine it. But the way that I do it is that I draw out, let's say this is the star right here. We see that that star is attached to this methyl group right here on the left. Instead of drawing that to the left like we did over here, I'm gonna push that methyl group going down like this, because this single bond can do free rotation. I'm just gonna push that single bond go down and make the new bond between the star and dot going in a zigzag form like that, like to keep that zigzag form in the main chain, like right there, right? And then that dot right here is attached to an ethyl group, which is this ethyl group right here. And I'm gonna draw that ethyl group right here, 1, 2, which is attached to an OR group and an O minus group right here. Does that make sense so far?
Yes.
Yeah, right. I like drawing it like this because this looks cleaner than this sterically hindered molecule here. But it's the same thing though.
Yeah, no, for sure.
Right. So now once we have this right here, this O minus here, we have to stop and see if we can kick out any leaving group, which we can. This is going to be the leaving group that we are going to kick out, right? But this is a bad leaving group, but it's still able to leave because we're in basic condition still. So we're going to reform our carbonyl, kick out that leaving group. And so that's going to give us this intermediate right here. But the bad leaving group is so unstable. It's unstable, it's angry, right? So it's going to look for vengeance in the mechanism. It's trying to get something to become neutral, become stable again. Right? So if this was predicted product, this would be your final answer. Right? The 1,3 dicarbonyl or the beta keto ester. But if this was mechanism, you don't stop here. Right? Because this bad leaving group here that left is very unhappy, very angry right now. It's gonna look for vengeance. So what that's gonna do is it's gonna grab the alpha hydrogen between the two carbonyls, giving that alpha carbon a negative charge. And this is the only irreversible step in the mechanism, because it doesn't want to go back to its unstable state. This OR minus here does not want to go back to the OR minus state. It wants to keep its hydrogen. It's like it's my hydrogen, and it's not giving that hydrogen back, making this the only irreversible step in the mechanism. And we would have a negative charge on the alpha carbon now. And then this is where we bring in the second step, the acid workup step, right? H plus workup, which is just going to neutralize the alpha carbon to become neutral. Final answer is that.
Okay.
A beta keto ester or a 1,3 dicarbonyl. To predict the product quickly, I'm gonna show you here, and then I'm gonna give you another example problem on that. So if this was self-Kleisen, actually let me do it here. Right. Star is the alpha carbon, you know that's gonna be your electrophile. Dot the carbonyl carbon, that's the electrophile. So draw out the star molecule out, nothing's going to change to the star molecule. The star molecule is going to keep all of its groups, right? So this is the exact same thing as this. I just shifted the methyl group of the star downwards, where when I make the new bond between the star and dot, this is the dot right here, the dot carbon will no longer have its OR group because of the mechanism. That OR group leaves, but the dot is still attached to everything else, like its carbonyl and its ethyl group like that. Right, so this is the new bond between the star and dot, but the dot no longer has its OR group.
Okay.
Right. Okay. Yeah. So that's how you predict the product quickly. I'm going to show you the 3 limitations for this now. The first limitation is the limitations. We cannot use OH minus as a base because that would do saponification or hydrolysis in basic conditions. Hydrolysis in basic conditions of the ester. So this is chapter 20. And give us this carboxylate here. We don't want that. We cannot use an OR minus where the OR minus is a different OR group because that would do trans esterification. Trans esterification. Right. Like let's say we use NaO, CH2, 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 CH3. That's not going to do this Claisen condensation mechanism. It's going to make a different ester. It's going to make that ester right there. With that OR group. All right, that's also chapter 20 reaction. But then if we have excess of that, then once we do trans esterification, we can do Claisen condensation after we match the OR groups, right? The OR group of the ester here has to match with the OR group of the reagent. The third limitation is that we need to have, this is the most important limitation probably. This reaction needs at least 2 alpha hydrogens to proceed. Where the first alpha hydrogen's job is to generate enolate ion nucleophile, generate the nucleophile of the mechanism. And I'll show you that in the mechanism that we just did. The second alpha hydrogen's job is to quench the bad leaving group, looking for its vengeance. Right. So this is the first alpha hydrogen right here that got deprotonated to generate this nucleophilic enolate ion. That's the job of the first alpha hydrogen, to generate the nucleophilic enolate ion. Then somewhere in the mechanism, when we kick out the bad leaving group looking for its vengeance, the second alpha hydrogen on the same carbon is used to quench the bad leaving group to become a happy leaving group. Right? If that second alpha hydrogen was not there and we had an R group, then something else is going to happen. There's going to be no reaction for Claisen condensation. If no second alpha hydrogen, we're going to get retro Claisen condensation. We're going to go backwards. Retro Claisen condensation, aka no reaction for the regular Claisen condensation. No reaction for regular reaction. Right. Okay, so that should give you a overview of what chapter 23 is. Do you have any questions on that?
No, thank you.
Yeah, no problem, Pimela. Okay. Okay. So, hey, Johanna, let's go over your quiz questions. Right here. Let's see. This one. This one, this one, this one. Okay. Okay. Did you want to go over all of this, or did you have a specific part in mind?
The second and mostly third
Mhm.
question.
Okay. Okay. Yes. When under basic conditions, the rate of the reaction increases substantially. Diagram the mechanism for the reaction with hydroxide as the nucleophile and explain the role of the base. So in basic conditions, you will have negative charges in the environment, right? Like if you think of bases like OH minus, OR minus, those are negatively charged molecules. Acidic conditions, we have positive charge environment, like H3O plus hydronium ion. Even if it's neutral, like H2SO4, there's partial positive hydrogens floating around. So basic conditions, negative. Acidic conditions, positive. Diagram the mechanism for the reaction with hydroxide, OH minus, as the nucleophile, and explain the role of the base. So a nucleophile, that term means nucleus for the nucleo part, right? Nucleo is the nucleus part, and phile is lover of. So a nucleophile is nucleus loving. And in Gen Chem, we talked about how the nucleus is composed of protons and neutrons, where overall the charge of the nucleus is positively charged because neutrons have no charge, they're neutral. Protons are positively charged, so if you add the net charge of a proton and neutron, it's positive. Nucleophiles love positive charges. Positive charges, they to negative charge, partial negative charge. That's the nucleophile. Wait, I think, let's see, I don't know. I think I'm lagging off right now because like my Zoom is delayed. Am I cutting off for you guys, or is this fine now?
It was lagging, but it's fine now.
Okay. Let's get. So a nucleophile is to be negatively charged because they love positive charges, and opposite charges attract. Right. So if they love positive charge, they have to be negative charge because opposite charges attract each other. The opposite of a nucleophile is an electrophile, right? Which means electron loving. What charge do you think an electrophile would have based on the name?
A negative?
So they love negative charge because electrons are negatively charged, right? And if they love negative charges, they have to be the opposite charge of a negative charge.
Positive.
Right, positive charge, right. So electrophiles would positive charges. It's kind of counterintuitive because the name sounds negative because electro is in it, right? Like, so you think of negative charge because of the electrons, but you have to think of the word phile here, like lover of the negative charge. So it's not an electron, it's a lover of the electrons, which means that it's opposite of the electrons, positive charge. Right. Even for nucleus, like even though nucleus is in the name and you think nucleus is positive charge, nucleophiles are not positive charge. They're negatively charged because they love nucleophiles. Right. So this OH minus here is our nucleophile because that OH minus has the full negative charge. This carbon right here, directly attached to the electronegative bromine, is partial positive charge. So that carbon right there would be considered our electrophile. And in OChem, for sn2 reactions, sn1 reactions, you'll see that nucleophiles will attack electrophiles. Right, make a new bond to the electrophile. Right, so this OH minus is the nucleophile because it has the negative charge. This carbon here that is partial positive charge is the electrophile. This oxygen here with 3 pairs of electrons is going to use one of its pairs of electrons to attack that carbon right there, to try to make a new bond between that carbon and the oxygen that has that pair of electrons. But when we do that, we're going to break the octet rule because there's 2 invisible hydrogens, which I'm going to draw out like that, which means that this carbon already has 4 bonds. 1, 2, 3, 4. Right? When this oxygen here tries to make a new bond with that carbon will have 5 bonds. That breaks the octet rule. And that's not good. So to conserve the octet rule, we have to kick out another bond when we try to make that new bond between the nucleophile and electrophile. And the bond that we kick out is going to be the group that is a good leaving group. And the good leaving group here is going to be that bromine right there, right? That bromine is going to leave, good leaving group, is going to leave with that bond right there. This bond right here is going to leave with the bromine. And have you learned about the term leaving group yet, and what makes a good leaving group and bad leaving group, Johanna?
Yeah, we had like a table he provided with us. So like usually like halogens like chlorine, iodine,
Yeah.
bromine, CN.
Yeah. Right. That list that you have are the list of good leaving groups that will leave with these reactions. And the reason why they are good leaving groups is when they leave with that pair of electrons from the bond, right? When they leave with those electrons, they could stabilize those electrons. So before, this bromine has 3 pairs of electrons, 1, 2, 3 pairs. But when it leaves with an extra pair of electrons from this bond that leaves with it. So that would make this bromine a negative charge. This bromine with a negative charge here is a good leaving group because it could hold that negative charge well, since that bromine is electronegative, right? That high electronegativity of the bromine allows bromine to hold that negative charge well. So when we see the product here, the way that you could see the connection is that you can star your nucleophile, which is this oxygen atom, and dot the electrophile, which is that carbon being attacked right there. And you're always going to make a new bond between a star and dot. So this is the dot right here. This is the star right here. And this is the new bond that we formed between the star and dot, where that bond right there has 2 electrons, right? Those 2 electrons came from one of the pairs of electrons on oxygen right here, right? One of the pairs of electrons on oxygen is one of its, like one of the pairs of electrons on oxygen went out to attack that carbon, which is this bond, new bond right there, like that. Oxygen still has its other 2 pairs of electrons right here, 1, 2. Right? But now this oxygen is no longer negative charge because it has 2 bonds now, 1, 2. Before, the OH minus here only had 1 bond. And then the side product here would be the Br minus that we kicked out. Right? Before this, Br minus was attached to this carbon, but it got kicked out in the mechanism. Any questions on this mechanism?
No, I understand it. So with number 1, he said that H2O was not a great nucleophile. Can you
Right.
explain what he means, like a little bit?
Yeah. So for the second part here, explain the Roller base, OH minus is a better nucleophile. H2O is not a great nucleophile. So if we compare the nucleophile of, let's say, H2O versus OH minus. The definition of a nucleophile is that it is negatively charged and loves electrophiles. They attack electrophiles. We see that water here is neutral. There's no full formal charge. It's neutral. Whereas OH minus here has a full formal charge of -1, making that the strong nucleophile. Right. This neutral molecule here is not a great nucleophile because it's neutral. It's stable. Right. Another way you can think about it is that nucleophiles, they are unstable with a negative. Right. What makes a great nucleophile is that they have to be unstable and reactive. Right. Strong nucleophile is reactive and unstable. Unstable. And we learned that something with a formal charge is less stable than something that is neutral. Right. So this OH minus here with a full negative charge of 1 is less stable than this neutral water molecule here. And because this is less stable, it is more reactive, right? Less stable, making it more reactive, making this stronger nucleophile, right? Because that nucleophile is more reactive, it is ready to attack an electrophile. more ready to attack an electrophile. Whereas the water here, more stable, since it has a neutral charge, formal charge, more stable. It's stable, it's happy, it's at peace. It is less reactive, making it a weaker electrophile, a poor nucleophile. Oh, like nucleophile, not electrophile. Weaker nucleophile. But it's still considered a nucleophile overall because the partial charge of oxygen is partial negative. Full charge of negative, but partial charge of negative, since it's more electronegative than hydrogen. But it's still considered a weak nucleophile because it's not a full negative charge like OH minus is. OH minus has the full negative charge that you could use to attack.
Makes sense. Thank you.
Yeah, no problem. Okay, so now for number 3, methyl terbutyl ether was a gasoline additive from the 1980s until it was replaced by ethanol in 2005. Proposed a reaction for methyl terbutyl ether using an alkyl bromide and alcohol with heating for an sn1 mechanism. sn1 mechanism. So sn1 is going to be multiple steps. It's going to have the leaving group leave first. So a mechanism for methyl terbutyl ether. Yep. Yeah. Okay, alkyl bromide and alcohol. Okay. So they're asking us to form or synthesize this ether here from an alkyl bromide in sn2 reaction. And I mean sn1 reaction. Right. Where in sn1 there's going to be multiple steps. Right. Where you're going to have a good leaving group present, and sn1 is going to use poor nucleophiles, like either water or some alcohol. Water or some neutral alcohol, ROH. Not OR minus, but ROH, neutral alcohol. The very first step of the sn1 mechanism is to kick out the leaving group. When the leaving group leaves, it leaves with a negative charge. And this carbon here that lost a bond is going to be positive charge. Right? And then that positive charge will be attacked by whatever nucleophile we have here. Let's say we had alcohol, and alcohol was ethanol, like this alcohol here. Right? Is this alcohol? Our nucleophile here is this oxygen with its pair of electrons that would attack that carbon there with a positive charge. And that's going to create this new bond between, let's say this is the star atom, this is the dot atom. This is the star atom, this is the dot atom. This is the new bond between the star and dot, right? And this carbon here that was positive charged before is now neutral because it gained the bond. This oxygen here that is starred is attached to an ethyl group and a hydrogen. And before it had 2 pairs of electrons, but now it only has 1 pair of electrons because it used its other pair of electrons to make that new bond between that carbon and oxygen right there. And because this oxygen has 3 bonds, it will have a positive charge. Right, it's oxygen with 3 bonds and a pair of electrons, but we want to get rid of that positive charge. So to get rid of that positive charge, we have to get rid of this hydrogen and give the oxygen a pair of electrons. So to do that, we have to use another equivalent of alcohol. The first equivalent, like the first mole you could think of alcohol, and then this is the second equivalent or second mole of alcohol. And that's going to be our base, right? The last step here of SN1 is always an acid-base reaction if you are going to neutralize this positive charge oxygen. This base here is going to grab that hydrogen. The oxygen is going to grab the hydrogen. The bond between this oxygen and is going to break and go onto the oxygen right there. And then that's going to give us this neutral product right there. Right. This last step here is always confusing because when you first learn it, the reason why we do that is to get rid of that positive charge. And to do that, we have to deprotonate it, right? We have to give this oxygen a pair of electrons and get rid of that hydrogen. To do that, we have to bring in the second equivalent of alcohol. Does that make sense, or did you need more explanation on like any mechanism here?
Yeah, that makes sense. Because so I think where I get confused is deprotonating OH into
Yeah, this part, right?
H2O.
The last part right here, deprotonating it.
Yeah.
Right.
So where's that
Uh-huh.
alcohol group coming for? Are we just that one?
This one here, this one will be given to us. Like, let's say, like for an example, they give us that alcohol.
Oh, okay.
Will be the nucleophile. Like I'm saying, like this ROH here is that right there. When the leaving group leaves, we form that carbocation. We use whatever they give us to attack that carbocation, giving us this intermediate here. Like, does that part make sense? Like that part of the mechanism?
Yeah.
Yeah, right. Once we get this part of the mechanism, we have a positive charge on that oxygen, but that's unstable because anything with a charge is unstable. So to get rid of that positive charge, we have to deprotonate it using a base. And the base is just another version of this you can think of because we have a lot of this in the environment. We have a lot of alcohol in the solution, like millions of them, like that. Another one is just going to come by, grab the hydrogen, and then as it's being grabbed, the bond between the hydrogen and oxygen is going to break and go onto the oxygen right there, right? Where this oxygen here, you still have only one pair of electrons, but now it will have two pairs of electrons. And it gained that extra pair of electrons from that bond right there that broke. Because that bond has two electrons, those two electrons are going to break and go onto the oxygen right there, making it neutral now.
All right, makes sense.
Yeah, you can include the side product if you want, which is this acid, right? Because this is the alcohol that grabbed the hydrogen, which is extra hydrogen right there. And because oxygen has three bonds, it's positive charge. But that's not the major product we're worried about. The major product we're worried about is this sn1 product here. Yeah. Okay. So if we go back to this mechanism here, the answer, the question asked us to form this by sn1 from alkyl halide. So you notice how we formed a carbocation in the intermediate right here? The carbocation to increase its stability as it's more substituted, as it has more friends you could think of, right? More groups attached to it. So most stable carbocation because, well, for now, when you learn about alkenes, you're going to learn that the allylic carbocations are more stable, but for now, the more substituted carbocation is the more stable carbocation. The carbocation with more friends around it is less lonely, more happy, more stable. Right. So we don't want to form primary or methyl carbocation. That would give no reaction for sn1 or E1 reactions. So if this was our product right here, our carbocation could have been this carbon or it could have been this carbon. Which carbocation do you think was in intermediate? Which one do you think was more stable?
The one to the left?
Yeah, the one to the left because it's more substituted. So we're going to make that split between them, right? Where the one to the left, if that was the carbocation before, it had a bromine attached to it, a halogen attached to it. And this thing right here, the CH3O, was the alcohol, right? So if I highlighted this portion of the molecule, that's this portion of the reactant. If I highlight this portion of the molecule, that's this portion of the reagent. So the first step of the mechanism, kick out the bromine leaving group, form the carbocation of that carbon that lost the bond, but I'm going to draw that carbon in this format, right? Where this purple carbon is the exact same purple carbon as that. But it no longer has 4 bonds because we kicked out that bromine. It has only 3 bonds now. And because it lost the bond, it has a positive charge. And this is what we call a carbocation, right? And this carbocation is tertiary, very stable. So now we bring in the alcohol, CH3OH, to attack, where the oxygen with the pair of electrons is the nucleophile that will attack that carbon. And that's going to make this structure here. where if this is my dot carbon right there, and let's say this is my star carbon, I mean star atom, this is the new bond between them. And then what can we do to neutralize this positive charge oxygen? What can we do to get rid of that positive charge?
Alcohol, right?
Yeah, bring in another alcohol, right? And that alcohol is going to act as the base to grab that hydrogen. And then as that hydrogen is being grabbed, the bond between them, the hydrogen and oxygen, is going to break and give that oxygen a pair of electrons, resulting in the final product there.
All right, I see it now. Yeah.
Yeah, that's good. That's good. The most confusing part of this mechanism when you first learn it is always this last part here, right? When you're deprotonating it, because like you said, like you didn't know where this came from, and these arrows might be confusing when you draw them out in mechanism, right? When the base grabs the hydrogen, the bond between the hydrogen being grabbed and what it was attached to, those two electrons are going to break and go on to that oxygen, right? Giving it the oxygen the extra pair of electrons, which is why this oxygen is now neutral, because it has two pairs of electrons and two bonds now. Like that.
Makes sense. Thank you.
Yeah, no problem. Have you learned about E2, E1 reactions yet, or just SN2, SN1 right now?
No, we are
Or
learning about E2, E1. I'm
oh,
just
but
behind.
yeah, just learning SN2, SN1. Yeah, that's good. That's good.
No, we're doing E1 and E2 as well. I'm just behind.
I see. I see. Yeah, but your next test is on December 6th, right? December 6th.
Yeah.
Yeah, that's good. That's good. And then you're showing up here as well, so that's good. Um, hey Zinyan,
Hi, Brian.
how are you?
Good, how are you?
I'm doing fine. How are you in material so far? Like, what part of 1C are you on right now?
Uh, I'm still on chapter 22.
Oh, chapter 22.
Yeah,
Let me see. Let me see if I could get the list of chapter 22 here.
it's benzenes.
Benzenes. Yes, yes, yes. Did you have a specific question that you wanted to go over, or did you want to go over a reaction, or?
Uh, he already gave us like a practice exam for
Yeah.
chapter 22,
Mhm.
and I just don't know what to do when he asks about like this stability or like the resonance of the benzene or like the reactivity of a benzene.
Oh, can you send me the file of the practice chapter 22 so we can
Okay.
see the problems? Yeah.
Sorry, just a quick question. Do you
Yeah.
have a list for the other chapters as well?
No, I don't. I just make chapter 23. Uh, wait, did I make chapter 23? Oh, I did, right here. Yeah. Chapter 23, right here. I didn't make
Oh,
chapter 24 yet.
okay, wait, I'm gonna take a photo.
Okay. Uh-huh.
Thank you.
Yeah. Helix, I mean not Helix. Farhat just started 24, right? Is he's still teaching 24?
Yeah, tomorrow's the last day of lecture though, for content.
Oh, so he's not covering chapter 25?
No,
I heard.
25 he starts Tuesday, but it's not gonna be on the exam.
Oh, really? So he's removing that because I heard chapter 25 was included in the next exam. So he might be
Or
removing that.
well, it's not gonna be on this exam.
Oh, not
It's
this exam.
just
Dang.
22, 23, and 24. Oh my God, you scared me for a second.
Really? Really? What the heck? Someone else told me something different. Like it's gonna be
Oh my
23,
God,
24, and
no.
25.
No, 25.
I sent it through email.
Let me see. Okay. Which problem specifically did you want to go over, Xinyan?
Oh, well, sorry, I didn't have my microphone on. Just the two right here, because I didn't find any other.
Oh, yes, yes, yes. This one right here, but which number did you have in specifically, or did you
Oh,
want
like
to?
the first two.
Oh, the first two, the first two. Okay, 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 okay. First two, first two. Yeah, yeah. Let's see. Two, 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 first two, right here. Okay. So, which ion would be most stabilized by resonance? So we have a positive charge here, a positive charge here, a positive charge here, and a positive charge here. So what's your thought process on this? How do you think about this problem here? Like what's your guess on this here?
Is it like the more resonance it can do, the better stabilized?
Yeah, more resonance, more stabilized, right?
Um,
And we're looking at the positive charges here, and which positive charge can do the most resonance?
is it the benzylic carbon? I mean, like
Yep, the benzylic carbon, which
yeah.
is this one right here, benzylic carbon, because that carbocation can do resonance with the ring, like this, and then it can go all around the ring. This is an sp3 roadblock blocking resonance, so that carbocation is stuck there, cannot do resonance, right? Whereas these positive charges here are on carbons that are already double bonded, and if those carbons are already double bonded, those carbocations are not on a p orbital. They're going to be on like an sp2 orbital, meaning that they are localized there. They cannot do resonance as well because the resonance is already occupied by the double bonds. The p orbital is already occupied by the double bonds of that atom. And this is like back to what I see in B, talking about which charge can do resonance. And it's the charges that are like in a parallel p orbital or sp2 orbitals or sp orbitals that are not on an sp3 atom, not on an sp3 atom, or not on an atom that is already double bonded like that. When this showed up when we talked about aromatic versus non-aromatic versus anti-aromatic, like the differences between this and this right here, and counting which pair of electrons counted as part of the resonance structure. Right, for this structure here, this counted, and that counted. But for the third one, the second one here, this counted, and this counted right there. But this pair of electrons does not count because that pair of electrons is on an atom that is already double bonded. It cannot do resonance with the ring. Whereas this double bond here is on an atom that has no double bond. It can resonance with the ring like that.
Okay.
Does that make sense?
Yeah.
Okay. So for the next one, which of the following resonance structures of the phenoxide anion would be the major contributor to the real structure? Okay, what's your thought process on this one?
Uh, I But like, I'm not sure what's it asking about, like the major contributor to the real structure?
Yeah, so all of these here are resonance structures of each other, of this right here. So if I draw out the resonance structures, like, they're just giving out all of the resonance structures of this structure like that.
Oh, okay. Oh, like
Right.
the whole?
Uh-huh. Yep, and they just keep going on to give all the resonance structures of this structure here. And they're asking you which one is the major resonance structure.
Is it the one with the anion on the O?
Yep, on the O, that's right. That's correct. And what's the reason why?
Because it's more electronegative.
Yep, the negative charge on the oxygen is more stable because oxygen is more electronegative. And there's another reason as well. Wait, let's see here. 1, 2, 3. 1, 2, 3, positive charge. 1, 2, 3. Yeah. Actually, all of these are aromatic still. So we don't break any aromaticity in the resonance structures. All of these structures are still aromatic, so we don't count the aromatic factor. We count the factor of electronegativity. That's it.
Okay.
Yeah.
Okay, so I know how to do this, but like, I think, well, we need to do benzene when we're doing like, wait, when do we need to do benzene?
Yeah. We need to do benzene whenever you have, so nucleophilic aromatic substitution. There's two types. The first type is going to be the one with two requirements. Well, both of these have two requirements. Like no, both of these will have the same requirement. They have to have a good leaving group on the benzene ring, on benzene, and you need at least one strong electron withdrawing group, ortho or para, to the good leaving group. And this is not the benzene one. This is something else. Just a regular nucleophilic aromatic substitution. You might see ipso substitution somewhere else. Ipso substitution. Right. The other type is with the benzene intermediate. It's very similar to that, but this one will have no EWG attached to it. You can see an EDG attached to it though. And this one will require a strong nucleophile, like the most common one, KNH2, NH3 liquid. We see that benzene, or NH water bicarbonate or carbonate Na2CO3 with high heat. Right, high heat is needed here. High heat. I think 340 degrees Celsius or something. Very like high heat. Extreme conditions. Right, so when you see one of these two reagents on a benzene with a good leaving group, you're gonna have benzene intermediate, KNH2, NH3, or NaOH with high heat. That's when you do benzene um, reaction, right?
Yeah, so like on benzenes, you can attack with the strong base, oh, yeah, strong nucleophile from like both sides of the benzene, right?
Yeah, both sides of the benzene, right?
Yeah, to get two products, but like I think there was a question about, I don't remember which one, but like how do you decide
Yeah,
on which one is the major product?
yeah. So that's if there is an EDG attached to it. Like let's say with an EDG like that, and we react this with KNH2, NH3 liquid, and I'm gonna draw the double bonds like this. The NH2 base, wait, actually, strong base. Yeah. Instead of strong nucleophile, let's say strong base, strong base, strong base. Like KNH2. NH2 minus is going to grab the hydrogen, make a bond there, kick out the leaving group, form the benzyne. Right, OCH3. Now we know that we have another equivalent of NH2 minus that can either attack this carbon of the benzyne or that carbon of the benzyne. We want the negative charge near this group right here because this oxygen is electronegative. It's an EWG by induction. So if we want the negative charge on this carbon here, which is the closest one, we are going to attack the other carbon, pushing the one of the bonds of the triple bond onto that carbon to get this intermediate here.
Sorry, why is the ether an EWG?
Okay.
Uh,
I so
yeah, it is an EWG by induction, but overall it's an EWG, EDG by resonance. By resonance. Right? Because it has pairs of electrons I can donate into the ring, but this oxygen is an EWG by induction because oxygen is more electronegative than carbon. So it's withdrawing electrons from the carbon inductively by just because oxygen is more electronegative than carbon. So it's naturally just withdrawing electrons.
Okay.
Right. But overall, OCH3 is considered an EDG because it could donate electrons into the ring directly by resonance. Right. But this is the factor that stabilizes the negative charge because this negative charge here would be withdrawn. Or like this oxygen here is high electronegativity will withdraw that negative charge towards itself. Does that make sense?
So does it wait, so the meta position is the minor one?
Major.
Oh wait, okay, never mind.
Right. Major, right? Because we want the negative charge close to it, so we have to protonate the negative charge to give us this final product here, giving us this major product. And the reason why it's major is because we want the negative charge close to this right here. Right? It looks counterintuitive because this is an EDG by resonance, but the oxygen just withdraws electrons from the negative charge, making it major, making the negative charge here stable, and that results in the major product here, meta major right here. Yeah. And the minor would be ortho because the negative charge would be too far away. Too far away. Yeah. Let's see. Oh, CH3, H2. Like if you think about the intermediate, which is going to be in purple, the intermediate of the major is more stable, closer to the EWG by induction. This negative charge is too far away by the EWG by induction, making it less stable, minor. Right? Did that make sense?
Yes.
Thank
Right.
you so
The
much.
negative charge here is not on the thing. Yeah, no problem. Yeah.
Do you need an acid workup or something to get rid of the negative charge? Or is oh no, never mind, it's already substituted?
Oh yeah, the acid workup comes from the solvent. So the solvent here is NH3 right here.
Okay, okay. Oh, okay, got it.
Yeah. Yeah. Okay.
Okay.
Yeah.
I like
Good luck on. See you guys. Bye.
Oh, okay. I like found one on the practice problems about the acidity and the reactivity. It's like 11.
Yeah.
I'm just like for those when you have like a lot of substituents on the benzene and it asks for like acidity or reactivity, I don't know how to look at it.
Reactivity. Yeah. I'll go over this in tomorrow's office hours at the beginning. This problem here first tomorrow.
Okay,
Yeah.
sure.
Yeah.
Okay, thank you.
Yeah, no problem, Xinyan. See ya tomorrow.
Good night. Bye.
Yeah, good night. Good night. See ya. Bye.